This tutorial is about using bisection method. In your manual, we have previously looked at the graphical method and how the root of this sextic function or sextic equation is around 1.5. But how do we further narrow it down? We can use bisection method, or we can use false position method, which is a little bit faster than bisection method. And these values are already written in the manual that we will be using. And a general procedure for both of these methods is given. So in this tutorial, we'll look at the bisection method, and in the next tutorial, we'll make that simple change to try the false position method as well. So what we want to do is, we have a bracket, we find the value of the function at each point of that bracket and see if the product is less than 0. If the product is less than 0, that means they have opposite signs, and that means the root lies between this little bracket. And then now we can, bisection means just let's go to the midpoint of this bracket as our estimate of the root. And then we figure out if this point has been calculated, is the value of the root on the left side or on the right side, because we have divided this bracket into two smaller brackets, and then we just figure out which smaller bracket has the root, and based on that we keep repeating this process until we converge to a single value, which basically means that the product of the lower and upper will be 0. Okay, so let's implement this. So again, this is our graphical method we just tried. Let's create a new script called bisection method. And we know that in our bisection method, we are going to have a lower value of 0.5 and an upper value of 2.5. And we also know that our acceptable tolerance for this method is 1%. Tolerance. Okay. And this one is our bracket. Okay. Now let's find the values of the function at these points. So values of function of the equation, values of f6 at bracket points. Okay, so of course we will have to call them something. So let's say we call this fyl and fyu, and these values are, of course, we take f6 function, which we have already defined here, and call this f6 function with these values of yl and yu. And now let's just check if this value, if the product is less than 0 or not. So for that, we learn a new command called if command, if end. So if there is a condition here, some condition, if that condition is satisfied, do something. Okay? That's a general definition of an if command. And so in our case, the condition is that if fyl multiplied by fyu is greater than 0. What we are saying is that if this product is not less than, so greater than or equal to, if this product is greater than or equal to 0, then we want to generate an error. And that can be generated by error command. And what we are saying that the bracket does not contain a root. That's basically the error, and you can always put an error in front of it. So if this condition was not satisfied, then that means you're on the same side, or either both of these are positive or both of these are negative, or it is equal to 0. in which case it is the root. Okay, and we can of course add that condition as well. But for now, let's say actually let's remove that. If it is greater than 0, then there is no root between in this bracket. Okay, so check validity of the bracket. Okay. Now, after this, we're gonna start the main loop and keep going through the loop until we can find the root. So at this point, you can decide whether to run the iteration for 100 times or 1,000 times, and it's a good idea to set a limit so that it doesn't keep running for infinite. So I'm going to run this for 100 times. Of course, it doesn't have to run for 100 times. It will stop whenever my error goes below 1%. Okay. And the first step is find new estimate. Okay. The second step is, and so this is a pseudocode that I'm writing to make sure that I understand what process is. Check error versus compare error to the tolerance. And stop if you have reached the tolerance, or create a new bracket based on if the root lies in YL, YR, or YR, YU. Okay? And that's pretty much it. And then keep repeating this process. So let's first put the equation for the new estimate, and this is given in your lab manual for the for the bisection method. Okay, so that's my new estimate, and now I want to compare with. So first I want to find the error, which is the approximate error, and I know approximate error is this new value minus some old value divided by the new value times 100. But what is the old value? What is the old value? So in our case, the old value is whatever I calculated at the previous step. And so in this case, I'll have to do two things. First of all, at the end, save the old value. So save the old value. And that I can do right here. I can say YR old is equal to YR. So when I come back to the new calculation, this old value will be available to calculate the error. And then the second thing I want to do is, well, what about the first time I'm coming in? First time I'm coming into this loop, I don't have an old value. And in that case, I want to also define that. And I can just use any of these values, YL or YU. So let's use YL. So now I have an initial value, and then this will keep calculating it. And then right here, I want to see if my error is less than 1%. What do I do if my error is less than 1%? I want to stop doing this process because I have achieved my goal. So all I have to do is say break. Break this for loop and go to the end of this, and right here I can say display my solution. So this is the solution that I will get, and also I can say display the solution and the error so that I know how much error was achieved for the solution. So this part I have done. The only thing that remains is updating the brackets. And here again I can write a if command where I can say if the function on left times function at the new estimate is less than 0, that means the solution lies in this bracket. So now FU should be replaced with yu should be replaced with yr, so I have a new smaller bracket. So in this case, yu is equal to yr. Okay. Else, if fyr times fyu is less than 0, so this is the second scenario, and in that case I want this to become the new lower limit of the bracket, so I will say yl becomes yr. Okay. And if both of these conditions are not satisfied, most likely the product is equal to 0, and so we have reached our solution. So we can just say, you know what, the error has become 0, and I can end the loop. So you can see this is a very lengthy if-else statement where I have a built-in second level if-else statement. A couple of things that we also want to do to make sure that this program runs is, first of all, we need to calculate the value of the function at the new estimate, and that would be fyr is equal to f6yr. And then if we go down and see how we have updated the value of yu or yl depending upon which case it was, so we should recalculate fyl and fyu just to make sure that those values are as well updated. So right here, let's write update fyl and fyu, and we can just copy paste the above code here, and because that's repeated, and now we can run this code. So go ahead and press run and see what happens. So it looks like it found 1.75 with an error of -14, which is the reason for that is because this is also taking into consideration negative errors, and that's a mistake because we only look at the absolute errors. ABS is the function that converts this into a positive number, and let's rerun this. So now you can see that it got us an error of 0.5%, which is less than 1% that we desired, and it gave us 1.5078. It will be interesting to see how long did it take for it to run. So if you look at the value of n, it looks like it took 8 iterations. So it didn't do this thing 100 times. It only did it 8 times, and by 8th iteration it had reached enough error that it broke out of the loop and reached here. And this is how you implement Newton-Raphson method. I would highly suggest you to do this a couple of times. The only thing that this method is applicable for any function. So if you had instead of this function some other function, all you have to change is these couple of lines here, and the same code is valid for any other function that you are trying to find the root for. The things that you can probably change is what tolerance. So let's say your tolerance was 0.1 and you reran it, and you can see now the accuracy has further increased, and in this case let's check n. It took it 11 iterations to run it. And why don't we improve our code and put n right here so we know how many iterations it took it to run. And now if you run it, you will see the answer, the error, and the number of iterations it took to run this code. But that concludes this tutorial.